This is another day of our WRRC seminar series, and today we are grateful to have Dr. Michael Cooney to present some of his cutting-edge research that he has done out here. Dr. Cooney did his college master's, bachelor's, and PhD from UC Davis, California. He did it in chemical engineering, and then he did his postdoctoral research in Lausanne, Switzerland, at the Swiss Federal Institute of Technology, and also at University of Queensland in Australia. And from there he came to be then he went on to be a lecturer at Manoa University in Australia again. And then from there he came to UH as a researcher. And then we are glad to have you today, and thank you very much. Dr. Cooney, please.
That's why you clap now. You won't clap at me. So actually, one correction, I did my BS at UC San Diego, but did that as a thanks a lot for having me. I'm really happy to get to talk here. And I'm going to talk about mainly this project, but a few at the end. And as I've got many partners in crime, I'd like to say, and I'll be introducing them as we go along. But the main thrust is high-rate anaerobic digestion of high-strength wastewaters, and that's pretty much where I really am focusing. So it's liquid waste streams, and I want to amplify the rate of anaerobic digestion to try to make it competitive with aerobic. And you're fighting against the advantage of having oxygen as an electron acceptor. When you go to anaerobic, you don't have it, so the rates of reaction are slower. So the way that you get around it is working at the catalyst level, increasing basically the active surface area of catalyst per unit reactor volume. And fundamentally, I work on that through the design of packing materials. But I've done a lot of demonstration projects which have helped re-gear my lab research to basically go back and fit in demonstrations that work. So, talk about a few of the lessons learned and some of the applications that we've done. And I'll mostly focus on anaerobic digestion. And then finish with a project with Roger Babcock where we're linking this with some aerobic things. That there is an example. That is the demonstration scale reactor we did down in Pacific Biodiesel. Designed it, then Pacific Biodiesel engineers fabricated it from our design. Gave me some money. They cost you some money, and then they installed it down at their grease trap waste processing facility. I'll talk about down at Sand Island. And Ken, sleep right there, actually, that's not Ken, that is the engineer from Pacific Biodiesel. Ken was there helping us run this during the actual summer. So, just to give you my perspective on how I approach wastewater treatment, not necessarily the way that you value it, it's the way that I look at it, and it drives me with the motivation of how I go about designing systems and working with companies. So my basic view, if you want to look at the value of wastewater, in a wastewater treatment plant, you basically have three streams coming in. You have the wastewater, can often range from 3 to 10 million gallons per day. You have an energy stream, you have an aeration stream. In the water, you have carbon coming in, you'll have electrons, you have ions, and you have pharmaceuticals. Now, wastewater stream, I look at water, carbon, electrons, ions, and pharmaceuticals. That's how I look at wastewater. That's what I think I see when I look at it. Coming out, you'll have electricity. You can, if you want to do a certain kind of human applications. You can extract treated water. You can extract ions and steroids, hormones, alphabetic compounds, and perforated chemicals, and so forth. And you can also get a biomass and a biogas, depending upon the kind of process you use, anaerobic, aerobic, or so forth. And the relative ratios of these particular components' outputs really varies upon the process technology, in particular the form of electron acceptance. So if you're going to go to anaerobic, I just like to do this diagram, not necessarily for this audience, but usually more lay people. So I like to point out, coming in, wastewater is very high, your energy stream is lower, and your aeration stream is much lower for anaerobic, but coming out is water, same, that's your biggest product. And I just kind of highlighted what I look at: biogas, ions, electricity, pharmaceuticals, and biomass, and I kind of rate how they are. Your predominant output is water. This is often overlooked. If you're looking at a value-added product, I'm looking to the day when water is the value-added product over all else, because it is the dominant mass. You certainly will get biogas anaerobic, and you get the other compounds, but they're not anywhere near the concentrations or masses that this aerobic, your energy and aeration streams are much bigger, same amount of water. Your output, your dominant output is still water. And you may get a little more get a lot more biomass, and then the other components are still relatively low. So biomass and water are your big outputs from aeration. The big inputs that really increase is energy and air. So I always come back to, from my perspective, the predominant product exiting the wastewater treatment plant in any logical productivity metric is treated wastewater. And what you're going to do, whether it has value, that's another story. We're probably entering into a new phase in wastewater treatment that starts to have value. But to me, that is the product coming out of wastewater treatment. Historically, it has not been given any value. It's usually treated as something negative that has to be treated to a certain level before you discharge it, that's for certain. There have been a lot of efforts to find undiscovered value. You know, there has been a big movement to look at the pharmaceuticals to recover nutrients and so forth. For the most part, I consider those to be searching for a needle in a haystack. They're just very low value. When you look at the amount of water going through, these are low concentrations. This is not really going to be a high profit margin effort. And I don't think there's ever going to be technology that makes it high profit. So I think that the treatment of wastewater today still remains driven by the regulatory implementation of fines to avoid discharge and not the recovery of value-added products. And this is just an example. This is the big bay down in Brazil where the Olympics are going to be held in 6 months. This is a picture taken in 2015. They're literally dumping raw sewage into the bay. And on our own islands, of course, we just had a lawsuit that is requiring a full upgrade of our wastewater facilities around the islands. The point I want to make is, unless you really implement fines, I think for the most part, people will just dump sewage in the rivers. This is just the reality of life. Whether it's in Brazil or in the United States, you really got to go to a lawsuit to get people to clean water. Because there just isn't any money in it unless you fine them. And then it's the avoidance of the fine that is the driver. So, with that in mind, what was going on down at the city of Biodiesel? So this was a collaborative research between us and them. I acknowledged Robert King and Kevin Harris from the city of Biodiesel, the student Ron Lopez has now left, Scott Higgins, a postdoc of mine, who's left, Ken, as I mentioned, and then Sam Ellington was also at the city of Biodiesel helped us. So down there, our goal was to actually evaluate the application of the anaerobic digestion for the treatment of the grease trap wastewater, not the grease trap waste, but the grease trap wastewater, as a means to reduce their discharge costs. So what their product is, they're trying to recover the brown grease from the grease trap waste. They are not interested in taking the grease trap waste whole and putting it in an anaerobic digester to get us a solid anaerobic digestion to get more biogas. They want to get the oil out to merge in with their yellow grease that they get from the fryers to take to their Big Island plant, and they just want to produce and distill it when they want to produce biodiesel. Their wastewater then on site is a waste stream that they have to release, and they get increasingly, whether it was in their plants in Oregon, the big driver was with the plants that they had in Oregon. They were anticipating in Hawaii there was going to be greater and greater costs to discharge, and they replaced the discharge with the amount of water, the COD level, the BOD5 level, and the TSS level. So that was the rationale. If we could do some research with them to help them reduce the cost of paying to get rid of their wastewater. That's going to increase the profit margin of the pre-existing process they have. They already have tipping fees to collect the grease trap waste. That's paying for the separation down at the Santa Ana facility. They're at marginal profits taking that brown grease, mixing with the yellow grease to produce biodiesel. If you can reduce their discharge costs, though, you increase that profit margin. And that works because they already have a business in place. You're not going into that grease trap waste trying to find a high-value product. they've already done it. You're just trying to treat the water to actually help them make a little more money off another pump. So basically, they go around and they pick up trucks. Ken will tell you about that if you'd like to ask. He did that in addition to his job with me. He was driving around part-time, picking up grease trap waste and grease traps all around the city. It is not a pretty business. It stinks quite a lot, and there's a whole storyline about where the grease traps are, how to get to them in the restaurants, what kind of condition they're in, who's cheating who, and so forth. But nonetheless, the drivers know the streets. They collect these grease trap waste, they break it down to Sand Island, and they separate it. Theoretically, they heat it up. And if you heat it up properly, you get a very nice clean water phase, which is very high strength wastewater. Very good for anaerobic digestion. You get the brown grease at the top, you get some solids down at the bottom, which is bone and grit. And you get a little food layer in there. They call it the rag layer, but that's really food particles that actually are soluble in oil. And they're kind of at the interface between the water and oil because they're usually amphiphilic to some degree. Bring that wastewater in. They're taking the brown grease to make biodiesel. The grease trap waste was going in. We did this in the lab with Ryan Lopez. They have a mixing tank where we're basically adjusting the pH, because this is pH 4. So it's very acidic. It's full of volatile organic acids. We bring it in, raise the pH to an appropriate level. And then at this point, we're just letting it flow over packed columns. 2 packed column reactors. We just let it flow by gravity filtration to a treated effluent. And all we're trying to do is knock down the VO5 and the TSS by 90% so their costs of discharge go down. Now, in reality, we packed the bed with biochar. We didn't have thin discs. This is an early diagram. We did similar. We published this work, and from this work, we designed the reactors that were done at full scale. Obviously, we looked at the grease trap wastewater, what its properties are. We're talking a pH around 4 to 4.5. The total COD is anywhere between 15 and 20 grams per liter. Soluble a little bit less. Total nitrogen, usually around 0.15 to 0.43 grams per liter. You have your phosphorus as well. The total volatile organic acids are fairly rich, 2.9, 4.3. Most of the organic carbon, accessible, readily accessible, is in the form of volatile organic acids, which is a great substrate for anaerobic digestion. And we have a very good ratio of total COD of nitrogen phosphorus as well as the COD of nitrogen soluble. Very good range that in the literature suggests this will be a very good waste stream for anaerobic digestion. Now we ran experiments in a lab on a packed column, different kind of densities, but this table I'm showing you is 25, which is a packed column. A system HRT 3, 2, in 1 day, 37 degrees. And what I want to show, most things, the COD reduction, we were getting up at an HRT just under 2 days, 92 to 95%, 92 total, 95% solid. That would drop down a little bit when we got down, lower the HRT to 1 day. And the total suspended solids was also reduction. No, I didn't plot it. And those numbers are obviously screwed up, so I apologize. So that was 75. Yeah, that number's not right. Oh, no. So up to 75%. The total suspended solids really dropped off when we lowered the HRT to 1. So we had to stay around 2 for industrial purposes. But we were getting 92, 95% COD reduction in the COD, and up to 75%. Ignore the negative numbers. That's on the reactor that's in the middle. This R2 is over the total system, so those negatives should not be there. That's a mistake. They just shouldn't be there. Now, we were looking at biochar, which is a material that I promote very heavily as a superb surface for biofilms, particularly anaerobic digesters. With Tao Yan, we went through and we would take, after doing these reactors, we would take out the biochar, fix it, took it in pieces with the SEM images. We find very beautiful colonies of biofilms along the biochar surface. And Tao went ahead and did a phylogenetic analysis for differential DGE, and he found superb communities for anaerobic digestion. It was a good methanogenic microbial community. And very broad community profiles for very, from acidogenesis, and methanogenesis. very good communities in those biofilms. And mind you, our feedstock is contaminated with bacteria. And that, which I'll show you some other results, that feedstock, the biofilm profile, the community profile, is very different than in the biofilms. So the biofilms have shown to be very good at basically hosting the community that builds up the methanogens, which is important because there's different growth rates between methanogens, acidogens, and acidogens. They work at different pHs, they have different growth rates, and they respond differently to feed nutrients. But it's a symbiotic community. You have to have the right proportions of all three to get a dynamic metabolism and get good CO2 reduction at faster rates. The biochar happens to be a tremendous, even some more data showing why I think it's a great surface to get those biofilms that are very robust and to get sturdy. The fluid flows with unsterilized meat. So from that, then with Pacific Biodiesel, we went to our engineers and we did a PID diagram. Kevin Harris did this for us. Then they constructed it in Oregon, and they basically shipped it. They built it in. Oh, these are but they build them in sections of threes, and then they disassemble it, ship it, and they rebuild it back together. So it's basically in cylinders that can ship in on a ship in a big cargo container. And then they just take them out on a forklift, and then they stand them up and put all three together. It's a very nice modular design. These end up being packed with biochar. I like it, and I promote it readily because these are modular designs that you can actually put 2 to 3 to 4 to 5 to 6, as many as you want them together. You can run some aerobically, you can run others anaerobically, you can reverse the flows up and down, however you want to do it. And the mixing tank is right there, and then basically you ship each unit separately, and you just bolt it together and put it on a concrete pad, and you don't have to worry about putting a permanent structure in place wherever you apply these things. And you can scale them small or large depending on how much wastewater. So we did that, we brought it down. This was the lab basic design. This is where they actually produce their grease-trap wastewater. These are the tanks where they initially heat them up, deliver them into trucks, and then that way load them. And they've replaced these with much better heating tanks. This is right across the street, which is where they have their own biodiesel storage containers. And we basically are using these two containers to store our feedstock and our waste. And then this reactor is put in place right there. So I don't have, this photo was taken before they actually built it, but they put that in place right behind us. So we had 59 days to run this thing. It's another story that they go all this money, all this effort to install this whole demo system for them, and they chose not to put staff on it to get trained. So it was up to us to run it. Ken did a heroic job during the summer to run it after it was installed, but we only had 59 days for startup and to evaluate it. It's 59 days. And usually it takes months and months and months to get a good, thriving anaerobic culture. But after 59 days, we were able to get a culture that was operating at 70% reduction in CO2. It was, and we had a headspace gas composition approaching 60 to 65% of the average headspace in methane. So we could burn it right on site. And the gas production rates were approaching the theoretical maximum based on CO2 reduction. So we took data all the way from July all the way through August. And that's our should be back. Ken did the tables right to left, and when I had to publish this, I had to go left to right. And this is one of the tables that should be there. I think, unless I missed something. Yep.
Why did they set 59 days? What was the rationale?
The rationale was at the end of day 59, Ken had to go back to school. And it's an off-campus facility, and he couldn't drive down anymore, and I was driving down on weekends and stuff. So it just was, you know, I offered the training, we offered the trainer staff, and offered them to keep going. And they just declined. They were also going through kind of a pretty tight financial crunch in the company, and they had a CEO there saying, "I want to take this just basically removing resources. So this did not become a priority. So we kind of, the staff, the guys with the boots, around, they were really good, they were interested in it. So when Ken had to go back to school, it was not really viable for us to be running something of that size on a day-to-day basis. We just couldn't go down.
But they let to run it after that.
That was the plan, but they didn't. It's now over on the Big Island, and they're not running it. It's one of those things that kind of didn't carry on as I thought it should have. We were trying to train one of their staff members in my lab, and that staff member had no intentions of ever doing that project. That was another problem. That's sort of why Ken came in to us. The person who was training had no interest in this project and didn't really tell us until about 10 years before it came and so on. So anyways, we had 59 days only, but the point I want to make is in 59 days to go from just starting, when we published this paper from the angle of this is a tremendous start. Because if you can actually go from day 0 to day 59 and get your culture operating with 70% reduction of CO2 on a high-strength wastewater, and you're already getting your methane headspace composition on average across all reactors above 60%, you really did well because we inoculated with sewage sludge. But we're feeding this thing wastewater that's fully contaminated with lactic acid bacteria and all that kind of cultures. We don't have any biofilms exactly the communities want. Well, Tao did it. This is just data to show that we actually got over time. This was a sample data, maybe 59 near the end. Across the entire reactor system, we have COD, total COD, soluble COD, and total voltaic acids. So they're all going down the match. The pH was going up across the system. So we had great, as the volatile organic acids are consumed, the pH goes up. So we got, the system was working very, very well as far as anaerobic petition should work. And Tao went through and he did a very extensive community assessment of all of the biochar across the entire reactor system. So MCO1 is mixed, the feedstock, MCO2 is the mixing tank, and then MCO3 was the first column biochar, and we treated effluent. So he went all through 3 spots in each column and the feed tank, the effluent, and so forth. And you did a community assessment, including the biofilms. And he found tremendous variation between the biofilm communities and the feed planktonic culture. And you can see going through, we had relative abundances, and we had somewhere around 33% advantages relative to the total population of the biochar biofilms. To get that after 59 days is very, very good. That's very, very good. So we were really happy after 59 days to get that good performance. And you can literally see, you open up the top and it's bubbling. It's like you're boiling water. It doesn't hit you. I can't tell you about that. So the gas production is very good. It's combustible gas. So I'm very confident this will work at any scale anywhere else. So I thought it was a success at that level. So we walked away. We have a paper published. They have their reactor system that they can work on any way they want. Summaries. Methanogenic archaea obviously grow much slower than acidic and acetogenic bacteria, and these differences are all obviously amplified by any number of process variables such as temperature, pH, and organic rate, whether or not it's sterile. The starting phase is very critical to long-term operation of anaerobic digesters, and a failure to achieve the right mix at the beginning can really lead to long-term failures or failures. And at lab scale, our biochar serves as an excellent packing material to support growth. Retention of biofilm is rich and active in healthy communities. And in this presentation, the same thing is shown in Excel at demonstration scale. And in just 15 days, we really got it. So I was very happy with that. So with all that done, where are we going now with this work in the research directions? So now, at Hawaii Kai, I have another demonstration facility, which is 6,000 gallons. And this was done through a company, Will Green Power, and that's primary clarified effluent. So now we're going to a very low strength wastewater, not a high strength. And our goal of this whole project in the beginning was to see if anaerobic digestion could replace aerobic-based treatment, because it's much, much lower energy. Can you replace the activated sludge beds by using anaerobic digestion to treat the anaerobic primary clarifier? Or could we significantly reduce the COD, or the BOD load onto activated sludge beds, and therefore reduce somehow the amount of aeration they have to put in the tanks? This was also based on lab work I did in the lab. And it was somewhat successful, but not tremendously successful. Part of the problem is it's just anaerobic digestion has a tough time getting really low in COD or BOD5. You can't really get down to EPA levels. It's really good at taking high strengths and knocking them down 90 to 95%, but it's really hard to get below 1 gram per liter. And we were dealing with stuff that's about 100 milligrams per liter. So it struggles to really reduce that. So, but it does knock it down 20 to 30%. So we brought in Roger, we had an advisory board at Econ and the White American Waters, and they suggested we talk to Roger. And Roger kind of designed for us, with the help of Krishna, his postdoc at that time, who's now a postdoc in Manoa. Well, I should say he's Roger's PhD student, he moved into postdoc, and now he's postdoc in Manoa. We designed trickling filters. So we have the anaerobic column reactor there, packed with biochar and other packing materials. The water flows up and through, and then it goes into a trickling bed filter, very low energy trickling filter. And we have the two together, and then we attached on the end a small sand filter. So we kind of evolved the design. It's still the same columns. We just actually took one of the columns, altered up, made a new trickling filter, and got rationing rings. Put them in. And this project was done with AECOM, Moving Power, White American Waters. Roger was a part of it, and also Lee Mansfield at AECOM, Dennis Tulang at Lee Mansfield, White American Waters, Dennis at AECOM. Rudy Minna helped sponsor this at AECOM, and then Dennis Furukawa was the person that we hired in Moving Power to actually build and install and run these. From which we did that. This is still running today after 3 years. So that's one of those deals where you work with the industry and it actually took off and people took care of it. That was great. I did not expect it to happen with this company. I expected it to happen with the other schools, but you just end up being surprised which goes and it doesn't. But that's part of the game of playing the industry. Local, especially small and medium companies. Sometimes they stay committed and sometimes they don't. So the basic design is the first anaerobic reactor. This is the primary clarifier effluent coming in. We have a range of packing materials, a big biochar nest in the middle. We had some hydrophobic bionest material that was designed in CETO. It's a filamentous ribbon that's hydrophobic. It's very good at taking it. It's designed to absorb out lipids and so forth, but it's not good for supporting biofilms. So in the middle, we have that in there kind of as a way because you do get some fog, and that's what increases leaching through the clarifier. So that sort of looks like it takes it out. We have a little nest at the top and just keep everything in place. The biochar kind of likes to flow out. And then it flows out over to the trickling filter. The rationing room's there, and we just have a recycle loop that goes in there. And what Krishna did, he came in here, Krishna designed for us, for a given series of HRTs, or hydraulic retention times through the system, he kind of worked through the recycle rates that would work for the treatment filter, or arranged to evaluate. And we also put on recycle on the anaerobic. And so then we went with that and looked at what the effluent. And the effluent does go through a small clarifier in the sink. Now what we found there is there are some conditions, and in case we found that we could get down as low as 7 hours. HRT 7 hours. And we were beating the EPA discharge requirements in both BOD5 and TSS over a moving average of over a month. So that was good. So that to us was, BOD was around 13 and TSS was about 8.5. That's after the sand filter. You have to have the clarifier and sand